So the main topic today is confirmatory factor analysis. But before we start the discussion about confirmatory factor analysis as an, I would say, alternative or structural equation modeling analogy to exploratory factor analysis, I would like briefly to recap previous discussion, and I would like also to go to some general rules for structural equation model building. So first of all, I would like to recap that path analysis model was, I would like to say, only set of regressions in which, for example, one dependent variable for the first regression could be independent variable for another regression. So here we have one regression model and the second regression model. I would like also to repeat that for path analysis, all variables in pictures, usually in squares or rectangles, are observed variables. So it means they are present in my data file. And I would like also to remind that previous terminology using expressions such as independent and dependent variable is changing here. So instead of independence, we are using the term they are exogenous. So these two variables exogenous, as there is no one-headed arrow included for these variables, and these variables with at least one single-headed arrow are called endogenous. Exogenous means they are not explained by the model. Endogenous means they are explained by the model. I would like also to repeat that for regression models as well as for path analysis models, if you have some endogenous variable, there is always some error which is attached to this variable. We call this as random error. And we would also estimate in structural equation models and the variance of these random errors. Variances of these random errors are just the opposite of variance that is explained of these endogenous variables by the model. So this is the portion of unexplained variance, and here we have a portion of explained variance. So this is the meaning of key terms and basic concepts in path analysis. And the last one recap from previous lecture says that in path analysis we can distinguish direct effects and also indirect effects. And if I sum up direct effect and indirect effect, I would get total effect. So that's all about path analysis. And now I would like to go into some basic rules for structural equation modeling, especially for those models that we called correlation, regression, and path analysis. So the rule one says that all independent variables, or we know that all variables that are called as exogenous, so all variances for these independent variables are estimated. So here for this picture, I would estimate variance for x1, x2 for first random error and for the second random error. So three variances will be estimated for this model. So this is the result of the first rule for structural equation modeling. Second rule says that if we have some, let's call it once again in older style, independence or in new style as exogenous variables, so all relationship for these variables are also estimated. So in spite of the fact there is no double-headed arrow here present, packages for structural equation models would automatically estimate also this relationship. If I would like not to estimate this relationship, we have two options, as you know from previous discussion. We can fix the value, for example, to 0, or we can also say that this relationship is the same as another relationship, so we can take equality sign for two or more relationships. So this would be possibility how we could avoid to estimation of this double-headed arrow. So it means a correlation or covariance for these exogenous or independent variables. So this is the second rule for building of structural equation models. And the third model for this introduction today, we would cover 3 more rules. So the third rule says that if I take some model, so I would take all possible coefficients between latent or observed variables if theory doesn't expect just opposite. So for example, here, according to this rule 3, not only these arrows would be present on my picture, but also this last one would be here. But as maybe the theory behind this picture says, there is no expected direct relationship for x2 and y2, so please don't use it. So once again, general rule says everything should be related, every variable should be related to each other. If the theory says opposite, so please don't use these relationships. So these are basic 3 rules that are mainly applied to simple models. So it means for correlation, regression, and path analysis. And today we would cover 3 more rules that are special for confirmatory factor analysis. So let's go forward and let's go to confirmatory factor analysis, or simply only CFA. So usually shortages such as EFA for exploratory factor analysis and CFA for confirmatory factor analysis are only applied. So you can find also in the literature that somebody applied CFA, and it means that he or she applied confirmatory factor analysis. So first of all, I would like to once again show you the picture, which is trying to explain the basic difference for exploratory model and confirmatory model. So on the left hand side here, you can see exploratory model. So I have some latent variables maybe behind my data, but I have 1, 2, 3, 4 manifest variables, and I'm trying to discover whether there could be something behind my data. So my question, first of all, is, can be some hidden dimension or dimensions behind my data? That's exploratory style of thinking. I do not have some precise idea, and I would like to create this precise idea. That's the exploration of my data. That's why I'm, for example, estimating this two-factor model. I'm estimating all these factor loadings. So once again, regression links for factor analysis are called factor loadings. So I'm estimating here 1, 2, 3, 4, 1, 2, 3, 4. So it means at total 8 factor loadings. And according to the values of these factor loadings, maybe I would decide that these 2 manifest variables, I1 and I2, are maybe creating something behind what could be called factor 1. And maybe these 2 items are creating factor 2 behind these variables. So I'm trying to prepare, I would call it, some theory, some hypothesis from exploration of my data. That's the meaning of exploratory factor analysis. For confirmatory factor analysis, I'm in, I would like to say, the second stage of my research. So maybe that somebody else, or maybe that I studied this phenomenon in previous research, and maybe that I set up hypothesis that first 2 items are creating first factor, and the third and fourth item is creating the second factor, and maybe that due to correlation for these factors, so it means by some oblique rotation, I also discovered that there could be also relationship for these two factors. So here I have some quite precise idea. I have two items closely related to one factor and two items to the second factor, and also relationship for these two factors. So it means correlation or covariance is present here. So this is quite a different picture from this one, as I do not expect this relationship. We usually call this relationship as cross-loading. So these loadings, two items of the second factor, I would call cross-loading. So no cross-loadings are present here, only loadings to items that are hidden in this common factor 1 and common factor 2. And I would like, and as far as you know about structural equation modeling, I would like to test or evaluate this model, this hypothesis. That's the meaning of confirmatory factor analysis. So I have quite strong idea about the pattern of my data, about presence of factors, and I would like to evaluate it by framework of structural equation modeling. As we can see pictures here, and for exploratory factor analysis, we have also discovered equations behind. So for this first introduction, I would like also to show you equations that are behind the scene. So here, as you can see, is 1, 2, 3, 4 regression equations. For all these regression equations, dependent variable is manifest variable I1 up to I4. So for example, the first equation would be I1 is based on the level of the factor 1, so it means some factor loadings multiplied by factor 1 value and plus random error. The second, the third, and the fourth regression equation would be written in the same style. I would like only to remind that usually these factor loadings in statistics are abbreviated as lambdas. So that's why we have here on slide 8 a set of equations. So I1 is equal to lambda 1, 1. So it means from the first item to the first factor, multiply by the first factor plus first random error. Here is missing part. So it means if I would switch from this confirmatory to this exploratory factor analysis for I1, I would also need to add the impact of the second factor. But for this confirmatory factor analysis, this cross-loading is missing. So here is the blank space for this missing part. The same style for I2. Once again, the impact of the first factor plus the second random error. So here it is. And once again, blank space for the impact of the second factor. Once again, there is no cross-loading from factor 2 to item I2. And the rest, very simple, items I3 and I4 related only to the second factor and random errors E3, E4. The main goal for confirmatory factor analysis is to evaluate the model. So it is slightly different from exploratory factor analysis. For exploratory factor analysis, we try to find these factor loadings, and we try to discover where there is 1 dimension, 2 dimensions, 3 dimensions, etc. For confirmatory factor analysis, first of all, I have some strong idea about the pattern of my data, and I would like to evaluate this pattern. So these factor loadings are not the main estimates for confirmatory factor analysis in comparison with exploratory factor analysis. So I would like to evaluate my model. You know that I can evaluate my model by testing. There is a chi-square test included in confirmatory factor analysis. And we know that especially for some special cases, sorry for that, I would only stop recording for a minute. And once again, the main goal is to evaluate model by testing, and we know that for bigger samples and as well as for slightly more complex models, we should also use alternative criteria such as CFI, TLI, RMSEA, SRMR, etc., etc. So once again, we would be using these criteria. And in the second step, we would also discuss about estimates of factor loadings and also about the rest of estimates that are present here for confirmatory factor analysis. So I would like only briefly to recap basic steps for the evaluation of models. So first of all, we would be using overall evaluation, and then we would be evaluating individual parameters. And today, we would also discuss option of so-called modification indices. So if I'm computing my model, there is also option in structural equation models to find whether there could be some change in my model that could help my model. So it means it would decrease chi-square test criteria and it would improve the quality of the model. And for these occasions, we are using so-called modification indices. We would discuss about these indices and about its usage at the end of our current model. So I would like also to remind that we are using criteria such as AGFI, NNFI, etc., but mostly we are using TLI and CFI values over 0.9 or something like sign of quality. For measurement of error, we are mostly using especially RMSEA values below 0.05 or maybe slightly more liberal recommendations, 0.08 or below are quite good. So this is the evaluation of the model, and we can also compare models by so-called information criteria. There are two well-known information criteria, and only these two are present in CHASP, so-called AIC and BIC. AIC stands for archaic information criteria, BIC for Bayesian information criteria. Here you have the formula for AIC, so it takes the value of chi-square test criteria and multiply by complexity of the model, so it means number of parameters minus 2 times degrees of freedom. The logic for the evaluation of these criteria is quite simple. The value which is smaller means that the model is better. And usually we find recommendation such as that the value of the difference as 10 points or more means much better model. For BIC, there are also some specialized recommendations, such as also difference 5 points or more is the sign of better model. So this is the evaluation of these differences. Here you have also the literature which is related to these recommendations. So that's about general evaluation of the model as a whole. And for evaluation of the parameters, we are using once again some statistical testing and also confidence intervals. Here we have the formulas, so parameter divided by standard error. This value is t-distributed variable. So by t-test, we can evaluate statistical significance of individual parameters. And if you like to compute confidence interval, you will take parameter and add or subtract 2 times standard error, and you would get 95% confidence interval. Fortunately, JASP would compute all this stuff for us, so it's not necessary for us to compute these by hand, but believe me, there are structural equation model packages and also in general statistical packages in which you need to apply these formulas by hand, so that's why you should also know how to compute it by hand. It's not very difficult at all. So that's the evaluation of parameters and the model we would like to evaluate here, and we would go step by step for this example of CFA is based on one factor model for well-being. So if you open JASP file, you should find items starting at the WB1. So this is the first item measuring well-being up to WB10. So there are 10 items measuring well-being. And my first question I would like to solve is whether I can apply one factor model, so it means all these items are measuring one dimension that could be called well-being. So this will be my first question. As the second question is, you can find it here on slide number 14, we would also briefly discuss about possible modifications. So maybe that it would be necessary slightly to change the model, but it would be the next step. And once again, we would be using here for these changes of our model, so-called modification indices. So that's the first insight into my data and into my example. And before we start, maybe you can go back into your memory from the lecture for exploratory factor analysis. And before we start to analyze data by factor analysis in JASP, there is one necessary step. We must somehow change the settings of our variables. Does anybody remember what is necessary to change for factor analysis?
We need to change it to scale.
Okay, so here, as you can see, these scales, and it's correct according to these labels. So these scales are defined as ordinal variables. So here we have three columns with different colors, but JASP currently performs factor analysis, doesn't matter whether it is exploratory or confirmatory, only for data that are cardinal or that are continuous scales. So before we start to changing scale, we should briefly discuss about consequences of these changes. So first of all, I would like to add that if we would like to be as correct as possible, instead of changing scale, we would try to find the software package that can handle ordinal data in factor analysis. What does it mean? So for classical factor analysis, doesn't matter whether it is exploratory or confirmatory, the basic computation, the first step before computation of factor analysis results is that this software package is computing correlations or covariances for all these variables. If these variables are cardinal, so it means long continuous scales, so usually this correlation is computed as Pearson's correlation, so it means classical correlation. But if these variables uses shorter scales, such as we have here, we know that if we are computing Pearson's correlations, so we would underestimate the level of relationship for these variables. That's why for these shorter scales, there are alternative formulas that are usually applied in exploratory as well as confirmatory factor analysis, or in general in structural equation modeling. Usually, we use correlations that are called polychoric correlations. Unfortunately, Jasper currently is not capable of these computations, but once again, we should know that the result will be slightly underestimation of these correlations. And if these correlations, which are base for computation, for factor analysis, will be underestimated, it means that our final results, doesn't matter once again whether it is exploratory or confirmatory factor analysis, will be once again slightly worse than that would be if we would apply correct correlations. So if we would change scales here, so it means I would click here and instead of ordinal, I would use scale, so it means cardinal variable, I know that my results will be slightly worse. So if I don't mind this, I would call it a slight decrease of quality of my solution. I could flow. If I would mind this problem, I would need to switch into some other package. In the next lecture, so it means in the next 2 weeks, we would be playing with M+ package, and this is one of options that could help us here. So in M+ package, we could ask for special algorithms for this computation with ordinal variables, and our results would be slightly better. But for this scale, also this change into scale variables wouldn't decrease the quality of the solution much, so we could follow this procedure. So it was only a small warning before the computation. I would like only to add that if your variables, so it means these indicators for factor analysis would be very, very short scales, so it means 2 values only, so it means binary or dichotomous data. So I would propose not to use these procedures, which are implemented, for example, in JAS or in SPSS, but you should switch into another package and you should compute it by correct computations. So here I will change it one by one. So for all 10 variables, it is necessary to redefine that these all would be treating as scales. So here we are. So these are our 10 variables, and for all these we can see here measurement scale. It would be possible for factor analysis, it doesn't matter whether it is exploratory or confirmatory, to compute results. If these scales would be defined as nominal or ordinal, JASP will not allow you to include variables into the solution. So that's the first step. The next step is to find a procedure for computation of confirmatory factor analysis. We have at least 2 options in JASP. We could once again ask for structural equation models, and here we would take structural equation modeling general approach, and it would be necessary to include Lavan comment syntax into the window which is present here in this dialog. So I would close it for today. We wouldn't need it. Fortunately, there is special option for confirmatory factor analysis, which is based on clicking management. So we could go into factor, and the last one option is confirmatory factor analysis. For most of tasks in confirmatory factor analysis, it is enough to use this very user-friendly part of the menu. For some special models, we should apply some different options in structural equation modeling settings. So here it is. So here we have confirmatory factor analysis dialog, and this is the same dialog as previous dialogs, for example, for exploratory factor analysis. So here we have the set of variables present in my data, and here I have one window, but as you will recognize next time, there are really more windows present here, and the first part of this window is called factor 1. So here it is expected that you would define individual factors, and if you would like to change the name of this factor, so for example here it is factor 1 and you would like to type well-being, so you can type well-being and the first factor would be called well-being. So you can change the name of this factor as the first step. Then you would take these variables, so it means WB1 up to WB10, and you can define these variables. We would skip this step at the beginning, and we would go into dialog downwards, and I would briefly discuss about options for this dialog for confirmatory factor analysis. So first of all, and it is slightly illogical, I must admit that the first option here is calling for so-called second order factor. So sometimes in factor analysis, so if I go back here to my picture, we can also expect that not only here factors are created by these items, but maybe that behind these factors, there is something like common factor for these two factors. And this factor would be called as second order factor. So sometimes, especially in psychometrics or educometrics, you can find these solutions. We wouldn't discuss about these second order factors, but if you would like to apply it, you can apply it here. So we would skip this option. Let's go to the next part, which is called model options. And here we have some special options. Some of these we will use today or maybe next week. But first of all, here I would like first of all to ask for change of factor scaling. We would discuss about this factor scaling in rule number 6. And we would be discussing about the necessity to set scale for factor, for latent variable. And I don't know why JASP is using factor variances as the basic style of factor scaling. Usually we use so-called marker variable scaling, so that's why I would change this style, and I will explain what does it mean in next minutes in outputs. So we would ask here for factor scalings, which is called marker variable. And this dialog for so-called residual covariances we will be also using today, and we would add some residual covariances in a few minutes, which will be based on recommendations on modification indices. So let's go back to model options. And next part, which is very important for us, is called additional output. And for this additional output, there are some parts that are very, very important for results. So first of all, I would ask for additional fit measures. I hope that you remember that we also asked for these additional fit measures in general structural equation modeling dialog. And if I ask for this additional fit measures, just add some fit indices, information criteria, etc. So you can see it here that 3 tables are added. So it could be important for us to find these CFIs, TLIs, RMSEAs, etc., etc. You can also ask for R-squared table. So it means that for every dependent variable here, it would be WB1 up to WB10, you would find the measurement of explained variance. So 10 R-squared would be present here. I would skip implied covariance and residual covariance. We will discuss briefly these topics next time. But here I would ask also for so-called modification indices. So this would add information, what could be the change in my model that could help to my model. You can see that by default, there is predefined cutoff 3.84. So maybe we should understand why 3.84 is present here, and maybe according to current recommendations, we should slightly increase this level. So first of all, you are familiar with the value of 1.96. What is 1.96 in statistics? What is the meaning of this value? Can you help me? Does anybody know about the meaning of 1.96 in statistics, or approximately 2? It is 97.5 percentile of standardized normal distribution, and we use usually this value for testing of statistical significance of t-tests, significance of regression coefficients, correlation coefficients, etc. And chi-square distribution, which is present here for basic testing, as you can see here, chi-square, degrees of freedom, and p-value is only the second power of standardized normal distribution, at least if you apply chi-square with 1 degree of freedom. And 1.96 squared is 3.84. So this value of 3.84 means that it would be testing on 5% significance level. Once again, current recommendations for structural equation models says that you should slightly increase this cutoff value, and usually value 10 is recommended in the literature. So I would ask for modification indices, and I would increase this cutoff to the difference of 10. And if I would like to see what is behind the scene, so it means what are commands of Lavan language, I can ask also for showing of Lavan syntax here. So this is additional output, one of the most important part. So we would skip multi-group CFA. We wouldn't perform such confirmatory factorialization, and we can also ask for plots. Here it is, and the basic plot, which is usually also published in books and articles, is classical plot for the model, and it is called model plot. Unfortunately, here you cannot ask to show the levels of individual parameters, but you can ask to show the description. So you can ask to show parameters. So I would ask for model plot and show parameters. And the last one option we wouldn't discuss today in detail says that by default you can ask here for computation of different estimation techniques. As you can see here, JESP will decide automatically by default if you wouldn't change this option. Here you can change the computation of confidence interval, and there is no necessity here, but if you have small samples and some special data, you can ask for robust or bootstrapped confidence interval. And the last one option, which is quite nice to ask, this is slightly different style from general structural equation modeling dialog, is to ask for standardization of your results. And usually we apply standardization of all variables. So you would ask for standardization all, and by the standardization all, the table with outputs, so it means for individual variables, would include also standardized results. So it is quite good to ask for these standardized results. So here we have defined all necessary parts. And the last step we would need to perform is to ask for computation. So I would take all these 10 variables and move it here to the first factor called well-being. So it would take some time to compute results and especially prepare charts. So we would need to wait for our results. And in a few seconds, or if it is bad, in some minutes, you would find your results. So I hope you can see at least some results for your model. maybe that you can see all results. At the end, you should find the picture. So here we have the picture. Unfortunately, this picture is using parameter estimates in unstandardized version, and there is no option here to change it. If you would like to change it, you could copy this model syntax, go into structural equation models, and for this general menu, structural equation models, you could find also picture with standardized results. So I don't know why it is not the same for these two options, but let's go to the evaluation of my model. Once again, I would like to recap that first of all, I would like to discuss about chi-square test and about individual criteria. So here it is. Here we have chi-square for our model, which is called factor model. It has the value of test statistics 167, so it means approximately 167 with 35 degrees of freedom, and the p-value is 0.000. And my question to all of you is, if it is good result or not, if I can see quite small p-value for testing of my assumption that I could apply this one factor model of well-being based on these 10 items. So what could be the conclusion from this chi-square testing here? Could somebody help me? So can somebody help?
That our model is statistically significant, that we can use it.
Once again, maybe slightly louder, sorry.
That we can use our model, it is statistically significant.
Once again, what are hypotheses behind this test? Null hypothesis says that my model fits to my data, or in other words, that correlation matrix from my model and correlation matrix from my data are close to each other. Alternative hypothesis says that my model doesn't fit to my data, or that correlation matrix which is generated by my model is not the same as a correlation matrix in my data. So what would be a conclusion from this chi-square test here? Be careful about that.
We cannot use it.
Yeah, we shouldn't use it as the p-value is very, very low, so we should reject this factor model. But once again, I would like to repeat well-known properties of this chi-square. So this test is quite good for small samples and for very simple models, such as correlation, regression, or some simple path analysis as we applied in the last computations. But for this model, so it means confirmatory factor analysis and maybe slightly more complex model, we know that this chi-square test is too conservative and it rejects nearly all possible models. So recommendation here is do not apply, do not treat, or at least don't use conclusions for this chi-square test. And that's why statisticians try to develop alternatives, and these alternatives are these additional fit measures and other criteria. So let's go to these additional fit measures. And first of all, here we have CFI and TLI. Once again, these are most common applied additional fit statistics. We can also ask to discuss about RMSEA, and there is also the value in the same table of SRMR. I would like only to say that these tables here in confirmatory factor analysis dialog here is slightly different from the organization of structural equation modeling output procedure, but still the values are the same. So CFI and TLI 0.883 and 0.85. Once again, if I go back to my presentation, 0.9 are recommended thresholds. So at least CFI and TLI doesn't follow, do not follow, sorry for that, these recommended thresholds. And also RMSEA below 0.08 is usually a very common recommendation, and once again it is slightly above this threshold. And SRMR below 0.05, once again slightly bigger value. We can see here 0.06. So maybe there are some problems present in my data. Once again, we cannot recognize these problems for chi-square test, as chi-square test is too sensitive for my model, but we can recognize it from these additional criteria. So our next goal is to identify what could be the problem of my model. So first of all, I would try to read individual results. So here we have parameter estimates. And maybe I can recognize some problems. And if this reading wouldn't help me, I would switch into next output, which would be called as modification indices. And we would find whether CHESP would help me to find some improvements in my model. So let's start to read these parameter estimates. So first of all, I would like to add that here for the first row, you can see that estimate is 1, standard error is 0, and there is no statistical evaluation for this first item. So it means here, as you can see it also here, there is no solid line here. So it means that this parameter is not estimated. The reason behind is that we need somehow to set the scale of this latent variable, and we decided to use the scale of the first item. So this setting was prepared here. If I go to these model options, so we ask here for factor scaling marker variable. Marker variable means that the first variable, first observed variable, will be fixed by this one factor loadings to latent variable. So this is the style of so-called marker variable factor scaling. There is another option once again, which is default for CHESP, called factor variances. If I would ask for these factor variances, CHESP would fix variance for this well-being as 1. So it would be different style of fixing or setting the scale of well-being. But this style of setting by 1 lambda fixed at the value of 1 is the most common. So that's why we applied this style of fixing. So this is only the meaning of this value 1 and no statistical evaluation. Here you have confidence interval 1, 1. So it means this is also not computed here. So this is the estimate which is fixed, so no estimation at all, and all the rest, so it means all these coefficients, so all these lambdas are estimated. So for example, if you can see 1.070, so it means that the second item, WB2, is related to well-being in nearly the same style as the first item. The third item is slightly more related to well-being, 1.4 times higher the lambda. For example, the first item is related to well-being slightly less in comparison with the first 0.6, 0.5 for fifths, and the highest relationship for well-being, latent variable, and one of these manifest variables is present here for the sixth item, and you can read the rest. Usually, for factor analysis, confirmatory as well as exploratory, we are not describing these unstandardized estimates, but we are using these standardized values. So it means values which are bounded by -1 and +1. So here we have standardized values. So usually we would read these values. So these 0.4, 0.5, etc., etc. So here you can recognize very simply that, for example, for the first item and for the fifth item, relationship of latent variable and these items number 4 and number 4 is quite weak. I would like to recap from discussion of exploratory factor analysis that if we are discussing about one factor solution, so you could take the square of these values, and square for these values is R square for these items. So if I would take the square of 0.3, approximately R square would be 0.1. So it means 10% of variance is explained for these two items, and the rest, 90%, is unexplained. So that's why usually you can find recommendations for factor analysis such as that these standardized factor loadings should be at least 0.5. So it means that explained variance should be for one factor solution at least 1/4, 0.25. So here at least two items could be problematic. So maybe that my first step to improve my model would be that I could somehow avoid to using these items number 4 and number 5. So it would be one possible change for my model. If I would like to check these computations of R squares, so I could go down, where is it? These are residual variances. So here it is up, and here you can see WB4 0.088. So once again, this is the second power of 0.297. And here 0.105, it is the second power of 0.325. So here we have the second power of these standardized estimates called R squares. These second powers could be used only if I have one factor. So for 2 factors, 3 factor solutions, it is slightly more complicated to compute R square. Once again, I would like to add that explained variance for factor solution is usually called communality. So these are communalities, and 1 minus these values are called uniqueness. So what is unexplained is called uniqueness. It is unique to it for individual item. So this is the meaning of these estimations or standardized estimations. And for all these estimations, not for the first one, as we described previously, you can find also statistical significance testing and confidence intervals. So you can also read these results. As you can find here, these all p-values are quite small one, so statistically significant relationship for all these individual items. So that's the first insight. You can find also here for these individual estimates residual variances. So it means, once again, if you go here, so for every dependent variable, I'm estimating the variance of random error. Here we have the figures. So these are unexplained variances, once again, unstandardized. And here we have standardized versions. So if you take these values, so this must be 1 minus these R squares. So 1 minus these values, or 1 minus second power for these values. So these 3 tables are related to each other. So here we have basic description. We know from previous discussion also that our model is not the best one according to CFI, TLI, RMSEA, etc., etc. We know that maybe we could exclude some items, such as item number 4, number 5. It would help, but we could also ask for so-called modification indices. So once again, if I go back, we asked for modification indices here in additional output option, and we asked to see only modification indices above 10. So that's why we have a quite short table here of so-called modification indices, and we can see some proposals for changes for my model here in this table. So it says that you could maybe add some link for random error of the third and fourth item. So we could add correlation or covariance here. We could also add relationship in the same style for item number 6 and item number 10. So here I would take item number 6 random error, item number 10 random error, and I could add the link. And there are some more recommendations. And now we would briefly discuss about the style of thinking and practicing of model changes with modification indices. So, first of all, if I ask for modification indices, I would find as the first the biggest value of so-called modification index. So this modification index is very simple to explain. So it would say if I would add, for example, this relationship, that my chi-square here for the first table would decrease by 43 points. So it means instead of 167, which is original value, it would get value slightly above 120. So it is quite big decrease. So it means quite big increase in the quality. 1/4 of chi-square would be eliminated, and only I would add one more parameter. So decrease of freedom would decrease only by 1 point. So maybe that CFI, TLI, and other criteria will be much better. I am not able to expect that p-value would be higher and that chi-square test would say my model could be the best. For factor analysis, this chi-square test one again is too conservative. So this is the meaning of this modification index. So 43 points or nearly 44 points in chi-square would be eliminated by this small change. If I am deciding about this change, it could be also somehow substantively important to add this relationship. So here, if I would ask to take correlation for these two random errors, it would mean that these two items, so it means original questions from questioner, are somehow substantively related. And they do not cover only well-being, but they also cover something else. So I would go into original questionnaire, I would read out the meaning for all these items, and I would like to find whether these two items could be somehow related. So it means they have also some special meaning together, which is not shared by all other items. So I can help you here that we have tried to follow this step, and according to specialists in this field, we decided to add this link. So my next model would add relationship for random error of the third and the fourth item. And the result is expected here in the last column called EPC. This shortage stands for expected parameter change. So it means that covariance for these two random error for item number 3 and item number 4 would be approximately 0.16. So this is covariance, and of course we are mainly interested in correlation. So we would maybe recognize the level of this correlation in next output. So here I would ask once again for copy of this previous analysis. So it would be the copy of this analysis. I would change the title. I would add link for random errors of WB4 and WB3. So it would be a change in my model. And this change could be performed here in model options. So here we can see the list of all individual variables in my model. And if I would like to add relationship for random error of the third and the fourth item, I would need to take these three items. So I can click on the first one, then control and click to the second one and link these random errors together. As you can see, Jasper will recompute my results, and after some minutes or seconds, so it depends on the quality of your processor, you would find results, and you could evaluate the second model, which could be at least slightly better than the previous one. So we didn't exclude any variable from my original solution, and we only add link to these two random errors for item number 3 and items number 4. So we could start the evaluation. As it was expected, chi-square should decrease by 44 points. So it means current value is 1, 2, 1, or 1, 2, 2. If I round up 122, which is quite low in comparison with the previous value. If you compare previous values of CFI and TLI and RMSEA, so here 0.883, 0.85, for RMSEA it is 0.089, and values for our slightly modified model 0.922, 0.897, or here for RMSEA 0.074, also SRMR 0.05 approximately. So all these values are following or nearly following recommendations. So maybe this model is better than previous one, and maybe that this model is acceptable. Once again, please do not try to conclude the quality of the model which is based on this chi-square test. So don't use for your conclusion these p-values. So that's quite good to see. You can also find our modified model is using this link for these two random errors. So here you can see the value 0.16. It was expected here in the table EPC 0.16. So all these computations are correct. And I can also go to our computations, and you can find it here that there is new one table called residual covariances, and this link for random error of item number 2, 3, and 4 is present here. Here's the estimate, standard error, etc. Unfortunately, I don't know why there is no information about standardized version, so it means about the correlation for these two random error link. It is not implemented currently in JASP. We can maybe ask just producers to implement it in next versions. So last one output we would go into is the next output, which is called once again modification indices, and there is one more recommendation to add some other links, such as item number 2 and item number 5 random errors should be related. Item number 6 and 10 random errors should be related. So we could also discuss about these modifications, but as we have tried to follow this task, we decided not to go further, so not to modify our model. So this model with only one small change, once again, relationship for these two random errors would be my final model, and I could apply this model for future computations. So it would be the final computation for today. So I